Okay, then let's continue. So two things remaining that are on my mind with regard to the question. Hello, can we continue? So with regard to this last question, one thing that came to my mind is, of course, Fourier series representations don't exist of all functions, but only of those functions that fulfill certain conditions, which are known as the Dirichlet conditions. And there are many functions that actually fulfill this, but not all of them. The other thing is with the PMFN stuff, there's also a lot of code. So if you really want to play with it, there's a lot of MATLAB code available that does all these things. So you can look at it in discrete Fourier transforms. So in terms of if you do it discretely on a computer, they always exist. Okay, then let's now continue with some applications of Fourier analysis and Fourier transforms in EEG. First thing, talking about filters and looking at filters in the frequency domain. So this shows a typical thing where Fourier representations or Fourier series representations are used to analyze, if you want, or at least represent some data. So here you would have some event-related potential waveform, and then, as previously mentioned, these can be basically then represented by the amplitudes or the respective frequency content. It's the same thing of varying frequencies, and what you should see here is that, of course, there's kind of a low frequency contribution to the signal, and there's something high frequency, namely this zigzag here on top of it, and this you can see here in the frequency domain, where you have a lot of frequency content or high weights for low frequency sine and cosine weights at the low end, but you also have this 60 Hertz peak, which is this additional activity or this added activity here. And any suggestions what this might be, this peak, why it's there? Yeah, so it's a typical example of line noise, so that the this EEG recording picked up some electrical activity, so alternating current activity from the power lines. Now I already again forgot whether 60 Hertz is the US or the European, because one of them is 50. US, thanks. The way one can look then at filtering or using filters is that filters essentially can be thought of as acting in the frequency domain and as weighting content in the frequency domain. So if you're talking about low pass filtering a signal, you can view that in the frequency domain you allow low frequency content to pass. So you essentially multiply the numbers that you have here with relatively high numbers, and you suppress higher frequencies by multiplying higher frequency content or higher frequency weights with lower numbers. So that's one way to think about filters. And then, of course, the specific form of a filter depends on how this function that you apply in the frequency domain looks. So if you, for example, would make this much quicker falling off, then of course you would not allow these frequencies between 20 and 40 to pass, so you would have a kind of a lower low pass filter. Of course, you can also do it the other way around, that you basically attenuate all low frequency content and at high frequencies pass, or that you do things like notch filters, where you let everything pass except, for example, this here at 60 Hertz. And the nomenclature, I think, will follow on a next slide. So if you apply this filter in the frequency domain, so you do the Fourier transformation, then you basically fiddle with the frequency representation and get a new frequency representation. Then if you reconstruct the time data based on this new frequency profile, in this case, because you let low frequencies pass and you set essentially the 60 Hertz to 0, you would get a time course that now doesn't contain the 60 Hertz component here anymore. It's actually fairly similar also if you think about, as I now use the word, if you think about ICA decompositions, they obviously don't necessarily lead to independent components that are of sine and cosine form, so usually not. But the idea of then getting rid of artifacts by first representing the original signal in some other space, for example with the independent components, and zeroing out certain that relate to eye movements, it's the same principle here, so that you project the data into a different space and you do something to this representation, and then you can reconstruct the data and the data looks different and then maybe more like you would like it to. So filtering out 60 Hertz of course makes sense because it's not a biological contribution, it's not coming from the brain. So this is the nomenclature that one needs a little bit of getting used to, but then it's quite clear. So high pass filters attenuate low frequencies and let high frequencies pass. Low pass filter, the inverse, so attenuation of high frequencies, passing of low frequencies. Band pass filters attenuate high and low frequencies, but let a specific frequency band pass. So for example, I don't know, 50 to 80 Hertz band pass filter would let everything between 50 and 80 Hertz through and mask out the other stuff. And then the notch filter that attenuates a narrow frequency band but lets all other frequencies pass. So if you draw, maybe it's always what I'm missing here a little bit, if you draw a bandpass filter function, then that would look like this. So you basically allow frequencies, so if this is here the frequency axis, you allow a certain band to pass, and a notch filter would look like this. So you let everything pass, but for a certain frequency. So for example, 60 Hertz. Looks as if I'm going to elementary school. Good. High pass filter. So when are these kind of filters used in EEG? So we already talked about high pass filtering data when we talked about data acquisition. One thing that happens, for example, during data acquisition is that one wants to avoid that the digitalization of amplitudes, of the potential amplitudes, gets saturated, so that the potential gets higher and higher, and at one point it just stays at the highest value that is encoded in the recording machine. So one can, to avoid these kind of very slow drifts, one can use a high pass filter. So these kind of linear drifts, you can think of very slow sine waves, and they are just on the increasing end of the sine wave, and then using a high pass filter with a certain cutoff at a very low frequency, here 0.1 Hertz, would remove this linear trend, so this increase, and just get everything to a nice and stable variation around 0. So that's high pass filtering. The question is always, and this is typical pre-processing question, how should I set my high pass filter, and what effect does it have? What's a good number for high pass filter? And the thing is, whenever you do something different in pre-processing, it will have an effect on your data. The question is, how much of an effect does it have, and mainly also does it affect the conclusions you draw from the data? So for example, does a difference between two conditions disappear suddenly after certain preprocessing settings in terms of filters or artifact corrections? So that there is an effect is kind of clear. The question is, what do you make of that? And yeah, this shows an example. So on the event-related potential waveforms, so unfiltered, you have kind of this black line, and then if you set your high-pass filter to increasing thresholds, so here you filter out everything that is below 1 Hertz, here between below 1.5 Hertz, and here below 1.1 Hertz, it attenuates the ERP amplitude. Of course, one can now think long why this might be the case, but in the end, this is just essentially the empirical finding. The thing is, in terms of here making a conclusion from this, this is something that Luck in his book did. In terms of making a conclusion from it, as the number of trials increases, the differences between the different forms of high-pass filtering actually disappear essentially, or get smaller, let's say. So the way I this question in terms of high-pass filtering, there first of all, there are social conventions, so you see in the papers of your peers what they do, and then you can always say, but they did it like that. But then they will say, but if they jump from a skyscraper, will you do it like that? So you should also have some idea, and then there are usually some methods papers that also discuss this. There was a recent discussion on filtering in EEG that a former PhD student looked a little bit into when he started his EEG data analysis. So sometimes these kind of discussions pop up in the literature where everybody knows that these things make a difference. At the same time, everybody knows that these differences, if one acts reasonable about them, one can deal with them, mainly by basically looking at a given data set, analyzing it with two different filter settings and seeing, okay, it doesn't abolish the stuff that I want to report, or it only abolishes it if I go to very weird filter settings, something like this. So usually these things are known in the community, but then you will have somebody who writes a paper that most of the EEG findings must be wrong because people do a weird filter setting, and then everybody goes a little bit crazy. And in reviews, you then for a year or so, you get kind of with this comment, isn't this double dipping? Isn't random field theory wrong? And so on, or isn't filter, isn't this, that, and then it goes away again. It's all social. It's all a social game, obviously. This is own data that we dealt with, and this now focuses on condition differences. So this was actually the checkerboard data, high and low frequency, high and low contrast presentations. So the dashed lines are the low contrast, the non-dashed lines are the high contrast. And this was actually in one of the scan years. The programming project had to do with analyzing EEG data, and people were supposed to actually analyze these data with different filter settings. And as you can see, the filter settings for the 0.1 Hertz, 1 Hertz, and 2 Hertz high pass filter cutoff make a difference. But as you can also see, the dashed lines kind of stay together, and the non-dashed lines stay together. So if you are interested in the difference between high and low contrast checkerboard responses in EEG, the filtering settings don't make a fundamental qualitative difference. Of course, they make a quantitative difference. Good. Yeah, low-pass filtering of EEG data. So that was all about high-pass filtering. Low-pass filtering of EEG data, what we already saw in the first image. Essentially the idea is that this removes high frequency noise and works as a kind of running average. The question is always with this, so the main thing about low pass filtering data is that it more looks nicer if it's a little bit smoother. That's a little bit like fMRI data smoothing. It looks more natural if it's like this. And of course this high frequency, it depends. I mean, we will discuss this also in MRI. If you are somebody who really believes that high frequency signals are really important for cognition, then of course you would not filter out this and make a story about what the high frequency content means. If you are, for example, interested in differences in here, I don't know, P300 amplitude, then you might say, this additional variation, this might be induced by some electrical activity, so we filter it out. And again, this is then social convention. Another aspect actually of, or where you also get quite strong low-pass filtering is just by the process of averaging, because if you have high frequency on a single trial variations, they are usually not very consistent over trials. So over many trials, they then cancel each other out, and you have a kind of internal low-pass filtering of data just by means of averaging. Same thing here. Here with low pass filtering, actually here, I think if you really, so nobody would do that, but if you really try to strongly low pass filter this data, then you can see that you can have quite strong attenuations, because at one point, of course, the waveform that you were describing as your event-related potential, which has maybe one peak or two peaks over 100 milliseconds, also has a frequency in the range of 10 to 20 hertz. And if you low pass filter with a cutoff of like 5 hertz or so, then of course you will also filter out your signal of interest. So standard low pass filters, I think, for EEG data are set to 40 hertz, so that you basically mask out all electrical ambient activity. But then, of course, you also cannot say something about 50 hertz oscillations or gamma oscillations, let's say, in the brain. Again, it's kind of, if you're interested in event-related potentials, then there's nothing wrong with using a 40 hertz low-pass filter. If you're interested in frequency, power spectra, and so on, then you might want to use not such a low cutoff for your low-pass filter. Notch filtering of EEG data for the removal of 50-60 hertz line noise. We've seen this. And then one can talk about these characterization of filters in the frequency domain on trying to quantify, basically give some numbers that characterize such a filter function. For example, the half amplitude cutoff. So that means if you have this kind of sigmoidal shape, that at here for 30 hertz you have a attenuation of 50%. And the same thing you would have here. So there's the difference is definitely here, this slope. Over how much, so they have the same half amplitude cutoff, but of course this increases much more smoothly than this, which stays up all the time, and then has quite a strong decrease. So you can describe these functions by the half amplitude cutoff. So when they are reduced by 50% and the slope, so the frequency amplitude decrease per frequency range. And these are then measured in decibel and frequency in octaves, but that's really not that. So if you discuss filters in EEG, you usually, I mean, it would be good practice to discuss, to specify more parameters of your filter. but usually, so filters can be implemented in many different ways. So they can be implemented in the Fourier domain. They can also be directly working on the data. There's a whole, I think for filters, this is something that I never really taught. So one can also make a full course, I think, on just filter theory and time processes. In the end, the main question is, in terms of analyzing EEG data and pre-processing EEG data, what are the filter cutoffs? And if you want to include more information on the filter settings that you use, just like always, include all your code in the analysis, and then everybody can look. Include all your code in your paper, so that everybody can look at it. And if people then want to know more about your filter settings, you don't have to write like long pages, but people can look it up in your code, and likely you use the default filter settings. So this is a little bit about filters. So the main thing here, this nomenclature, and a little bit of the use of high and low pass filters and their purposes in EEG analysis. Will come up again in MRI, where data is of course also filtered. And then, any questions about filters, except for the question, what are the best filter settings? No, also not really inviting questions. The last thing then in terms of frequency analysis is, I think, the more common type of analysis you see in cognitive neuroscience, where people are interested in EEG oscillations. So you have these labs that do oscillation studies, and that's what they do. And a little bit about what this is about. So the motivation, and this is what we saw yesterday, the motivation for looking at time frequency analysis is that although you might, over different trials, over a given condition at a given electrode site, you might have some consistent activity in terms of a frequency profile. So here you see these curves of different trials. If they are jittered in time due to all sorts of things, so for example that this is driven by a cognitive process, and this cognitive process sets on with some time jitter, I mean that's fairly idealistic. These non-phase locked activities, if you just do an event-related potential analysis, can cancel out, and you don't see phenomena that are of potential interest. One thing I have to say about this whole oscillation business, this always ends up with frequency content in terms of sine and cosine wave activity. And there is, except that sine waves go up and down, there is nothing fairly particular about sine waves and neural function. So people that deal with oscillations in cognitive neuroscience, they basically show that there are differences in frequency power, frequency content in different conditions. But it's not because they are talking about oscillations that they have a very clear idea about the underlying neural mechanism. This is sometimes always implied, and people are a little bit like, ERPs, but oscillations, this is really the neural activity, but it's not. So it's, of course, one can create neural models that create sine and cosine waves. One can also create neural models that create event-related potentials that don't have this prototypical sine wave form. So, don't let these people fool you that oscillations are somehow the most neurobiologically sensible thing. They are, from a data analysis point and from this kind of idea, they are a sensible thing to do, but it's not that this is, if you look at oscillations, this is the real neural activity or something. It's just one way to analyze and project EEG data. So what is time frequency analysis? Here trying some definitions. So so what time frequency analysis is about is basically to characterize the frequency content dynamics over some peristimulus time. Usually this happens at given electrode sites, so it's not that the entire data is now somehow integrated and evaluated, but this is again kind of electrode space data analysis. On a given electrode, you look at the time frequency pattern that is observed, and it's also, and this is what the second thing says, it's not one kind of analysis that people do, but there is a whole collection of tools that are used for time frequency analysis. And one thing that we will look at here is moving window Fourier analysis, where you basically do Fourier analysis in moving windows. There's because actually for lower frequency data you need longer data points to properly characterize them. There's also something called wavelet analysis, which uses different basis functions for different frequency ranges. So there is a whole zoo of wavelet methods that do the same thing. So they allow you to characterize frequency content over time, but do it a little bit better than windowed Fourier analysis. So when you read something about some oscillations, you, like always, you have to really look how they did the analysis. In the end, it will not change that much whether you use this wavelet with this basis function or this wavelet with this basis function, or you use a windowed time window Fourier analysis, but it definitely will make quantitative differences, but not necessarily qualitative differences. Good. So the way this then works is what we looked at here was that we have some time windows. So this was like, let's say 200 milliseconds or so, and this entire time course is then evaluated with respect to its frequency content, and the aim in time frequency analysis is to basically do this in not over the entire peristimulus time, but in a moving window. Yeah. So the idea would be that here you have on a given trial you have some time domain data, and you do in each of these time windows you do a frequency evaluation analysis, so essentially a Fourier transform, look at the frequency content over frequencies, and then once you've done this, you shift the time window and look at a next time window. And what this shows is the time domain signal as the black line, and as the dashed line the single trial frequency power. So on a single trial you see that the frequency power, so in the time domain you see nothing for some time, and then this oscillatory activity sets on and then it stops. And if you now look at the frequency content for this frequency, obviously, so the power at 10 Hertz, you see that once your time window encompasses the signal of interest, then the frequency power increases, then it stays up when the signal is happening, and then it decreases when it's done. And what this then also shows is if you now average together here the trial data, because these given trials, they are all here simulated to be out of phase, everything will be cancelled out. However, if you average together this frequency content, then something will remain. Of course, in this case, you could also just take the absolute value of the observed data and average this absolute value together. Then you would also get this power. So, but yeah, so the idea is again that you avoid this effect of cancelling out activity by looking at the frequency content and how it evolves over time. Now, with time frequency analysis, there's quite some terminology associated. So terms that always come up are the time frequency spectrum. So these are the time-specific measures of magnitude and phase over a range of frequencies, or better the frequencies of sine and cosine functions. There is what is referred to as power. Power is commonly just the square of the weighting coefficients for the sine and cosine functions, so that you, for example, if you have a sine wave contributing to your signal with an amplitude of 5, this is valued as much as something contributing with an amplitude of -5, hence the squaring, and then people call it power. It has really nothing to do at all with some physical notion of power. So it's just a measure of the magnitude. And then there are terms, and these are then quite important, namely the total spectral power, the evoked spectral power, and the induced spectral power. That's nice examination material, in the sense that these are terms that you will come across, and that people say, yeah, we're looking at evoked power here, we're looking at induced power, and it makes sense to know what this is. So the main differences here are between total spectral power, evoked spectral power, and induced spectral power. And to understand what these total, evoked, and induced mean, you just need to understand the data analysis that lies behind them. And that's what is shown here. So there are two things you can essentially do. So this would be the single electrode data that you observe on a single trial. So give an electrode in a single trial. And then you can, of course, do two things. You can take these single trial EEG epochs and average them together, like we seen before. So you get an event-related potential. And you can also on each trial do a time frequency decomposition. So this would then look something like this. So here you have a frequency on the x-axis, and you have frequency. Wait, this is a little bit confusing. Sorry, I was confused for a second. You have time on the x-axis. So this is exactly the same time scale as it is in the single trial EEG epoch. So you have time point 0 here and time point 1,000 milliseconds here. You have frequencies on the y-axis, and the content of these frequencies is encoded in terms of the color. So if you have like this blob here, that means there's large contribution of 10 hertz in this time window between, I don't know, 50 and 350 milliseconds post stimulus. Now, what is described here is that you can do time domain averaging, or you can transfer each of these single trial EEG epochs into a time frequency spectrum, and then you can look at the single trial time frequency spectra, and you can of course also average these single trial time frequency spectra together, which is shown here. Yeah. And I always hope that I actually thought that was a kind of a better representation. If you do this step first, so you first listen now carefully. If you do the time frequency decomposition on a single trial level, and then average these time frequency spectra over trials together, then you get what is referred to as total spectral power. So the squared magnitude values for each time frequency data point average over trials. Yeah, so you on each trial you do a time frequency decomposition, and you have these time frequency spectra, and then you average them. That's total spectral power. The evoked spectral power is what you get if you do the analysis this way. You first average all the time domain data and then do a time windowed Fourier transform of the ERP. Yeah, so that's essentially just what ERP means. You do a spectral decomposition of an event-related potential. And of course, in the event-related potential, you only have phase-locked frequencies because, or in the evoked spectral power, you only have phase-locked frequencies because in the ERP you only have phase-locked frequencies. So this is shown again here. So if you this activity, this early activity, this is in phase. Hence, if you have the ERP, you still see it. This activity here is of random phase. So if you average over it, you don't see it. Now, if you do this, and then doing the time frequency decomposition of this ERP gives what is called the evoked spectral power. Now, talking again about this random phase activity, here you see that this 10 Hertz activity here at 600 milliseconds or so, of course, shows up in all of the time frequency decompositions, and then if you average them together, it shows up in the total spectral power. And then the question is, the last thing, so essentially a total spectral power and evoked spectral power are really simple because total spectral power just means you do a time frequency decomposition on each trial and average the resulting time frequency spectra. And evoked spectral power is also simple because you just do a standard ERP analysis and do one time frequency analysis of the ERP. The only thing that one needs to be a little bit careful about is the induced spectral power, because sometimes people would refer to this total spectral power as induced spectral power. It would be a little bit cleaner if you would subtract from the total spectral power the evoked spectral power, because clearly you have this 10 Hertz activity here. So if you subtract the time frequency decomposition of this ERP from this average time frequency plot, so from the total spectral power, then you would only see the non-phase locked activity. Yeah, so here you have a mixture of phase locked activity, as you can see, because this was phase locked here. This shows up in the total spectral power, and non-phase lock activity. So this shows up here. If you're really interested in only the non-phase locked activity, so the stuff that you won't see in an event-related potential, then you should subtract the evoked spectral power or the evoked spectrum from the total spectrum, and then call this induced power. Of course, the term induced or evoked in natural language, they don't carry this meaning that you first do time frequency analysis and so on. It's just somebody decided that this would be a good nomenclature. So so the average of time frequency analysis of single trials contains both phase locked and non-phase locked activity, and hence it includes both evoked and the induced power proper. The time frequency analysis of a single trial average only includes the phase locked activity and hence the evoked power. So the last thing, as previously mentioned, is what you can do is to subtract from the total power the evoked power to only see the induced power if you want. Thing is, with induced power, again, you have to really look closely how people did their analysis. And in the end, all these terms like evoked, total, and induced don't really matter. The question is, how was the data processed? Was each single trial time frequency analyzed and then these time frequency spectra averaged, or was data in the time domain averaged and then the ERP time frequency analyzed? That's the important question. and the aim is again this aggregation of single trial oscillatory activity without any cancellation, so that you see potentially a little bit more than you would see in an ERP, but you still have some averaging process that allows you to minimize noise, because of course, even if you have random phase activity, this is sometimes stronger, sometimes less strong, and so averaging over time frequency spectra is a good thing. We've seen this. Frequency power, this is what you will always hear. So people will rarely refer to these things as weighting parameters of sine and cosine function. They always say there's so much, there's alpha power decrease, beta power decrease. Beta power is working memory. This is what people say. Did Bernie on Wednesday last week, did he talk about oscillatory activity, or did he talk about decision making only? No one remembers, because he in the old days he did a lot of beta power working memory, and as I tried to emphasize in the last bit, the order of averaging and time frequency analysis determines the power type. So if somebody asks you what's the difference between evoked and induced activity, you can say something like, well, evoked activity results from doing a Fourier time frequency analysis of the ERP, while induced results from averaging over time single trial time frequency analysis. As previously mentioned, it's not only Fourier transforms that are being used for this purpose, but also things like wavelets that adjust basically the basis function depending on where you are in frequency space. Convolution is also a signal processing tool. We will talk about convolution in MRI analysis, actually. So that was frequency analysis, what I wanted to say, and that was actually the end of this introduction to EEG. So we covered some ground. So this is what we did. Any questions on the last bit or the entire EEG course at this point? No. In terms of
is there, or can you give us some example for when do we look at ERPs and when we expect to frequency analysis?
No. No, the problem is that this is again something social. So in terms of, it's more like what you think is important about data. So you know that there are people that use pattern classification all the time, because they do. There are other people that do univariate analysis. There are other people that do biophysical modeling. It's essentially what you as a scientist think is important and what you grew up with, essentially. If you have good reason to believe, so if you want to discover something, let's say, so you say you want to make an academic career by discovering something novel, then of course you might not start with computing ERPs in response to a given stimulus, but you have the hope that by also looking into induced activity, you will find something. So basically, or let's say it differently. So you want to discover something novel. And then a typical thing is you do two conditions. People are, let's say, not conscious of your favorite stimulus, and they are conscious of the stimulus. And then you have some EEG data, and now you want to discover something. So then you would commonly start with doing an ERP analysis, because it's easy and it's the first thing that you're familiar with, and you understand because it's averaging. And then you might find differences between the ERPs in an electrode, and then you would say, oh, nice thing, let's report this, let's write a paper. Other thing that can happen is you don't find a difference in ERP analysis. Then you would say, well, maybe we should look at induced power, because we haven't yet, and maybe there's something that we didn't see there. And the other way, so that's one way of why you would do, for example, time frequency analysis. The other thing is that you want to continue on some phenomenon that has been described. For example, let's say somebody claims that better power at a given time window is related to working memory. You are interested in working memory. You now want to see whether working memory under some additional task constraints is still correlated with better power and changes, and the better power changes. So whether your better power also says something about this different task. So then you would start maybe out by doing time frequency analysis, or you go to a lab that always does time frequency analysis. Then you do time frequency analysis. So I don't see any principal reasons for doing any kind of data analysis, because you can do what you want essentially, but you of course always build when you start from somewhere, and then it depends on where you start. Personally, so in terms of neural modeling, so what I spent time on was to develop and contribute to the development of neural population models, like I showed you last Friday, that explain event-related potentials. And these kind of models also exist to model frequency data. One thing that maybe, but in a way you can also do that with time domain data, you can, if you assume that there are neural noise processes, so if you have random dynamical systems, they can be captured by time frequency representations without the need of doing full stochastic or random differential equation modeling. So there's a connection between time frequency spectra and probabilistic time series methods. So if you have a very strong reason to believe that you're interested in neuronal stochasticity, then you might be a little bit more on the frequency side. But yeah, so there is no principled reason to do one or the other, and time domain. So I would be very happy that in my academic life, or maybe my entire lifetime, I see some interesting neurocognitive analyses of time domain data. Even event-related averages, I would be happy, because they don't exist. I mean, what exists are all these comparative studies where in this condition the ERP looks like this, versus in this condition the ERP looks like this. But kind of neurocognitive, in terms of biophysical models and functional models, explanation of these differences don't exist. So I think cognitive neuroscience can still do a lot just by looking to the time domain. And of course, it's also more natural. So what I somehow don't like about the time frequency domain is that it's, depending on how you view it, but it projects the data already on some basis set, namely sine and cosine functions, that are there because you decide so. So I mean, why not triangular functions? So these kind of saw functions. Why not this form of wavelet and so on? It's already some kind of assumption that you put into your analysis without that good of a reason.
How do I interpret frequencies itself? Like, I mean, it's a high frequency or low frequency, but that's kind of it. In terms of neural activity.
Yeah, exactly. So that's something that. So of course, high frequency would mean that that there are some neural populations that go change the membrane potentials quickly over time. I mean, that's just what a high frequency means.
Which would mean like a higher rate of action potentials.
No. I mean, the whole thing is, of course, based on these dipole models, based on the extracellular potentials. So this is also important. So I would really, I wouldn't try to explain these kind of analysis in terms of neural thinking, because that's not what these analyses do. but people always seem to imply that, but it's just not. It's just looking at the sine wave or sine function content of a signal. Of course, you can come up with differential equation systems or any kind of dynamical systems that show oscillatory activity, but you can also come up with like we do when we do this ERP DCM with neural systems that show event-related potential activity. So thing is that simple systems maybe with so for very simple systems in physics, you can have these solutions that are then sine waves, but these are usually the solutions that are then without some more ecologically valid things like friction, where you have attenuating processes and so on. So I think what sometimes makes people believe that looking at oscillations has more to do with neural stuff are exactly these examples of simple second-order differential equation systems. But if you actually look at more realistic models of physical phenomena, they become less sine wave, cosine wave stuff. So, yeah. And of course, but the question is of course interesting, what are oscillatory systems, how do they look? That's something one can study. Yeah. But this is not implied by these analyses. And sometimes cognitive neuroscientists show you then a cartoon of some neural populations, and then they say here oscillations. So Ole Jensen is a typical example of that. Either you do the neural modeling and you do a quantitative, you set up quantitative dynamical systems that generate these oscillations, and you use these dynamical systems in the analysis of your data. Then I think you are doing something interesting, or something that is kind of makes sense. But if you just do a Fourier analysis and then start to talk about interacting neural populations, that's like Jakub Limanowski last week, who does GLM analysis of some hands turning around, and on the next slide he says, oh, we have this hierarchical model with the free energy and the active inference. This is not the analysis that you did. So it's a little bit of cheating to imply mechanistic ideas and conceptual ideas if you don't implement them properly in your data analysis. So because there are people who try to do both, and you basically cheat because you're just saying, oh, this is the same, and both people have 15 minutes to explain that, and it's a little bit of cheating. Anyway, any other questions? Because so I know Jakub, and it's nice, but he's one of these people who talk about the free energy principle without ever talking about free energy, or actually he's one of these people who say free energy principle when they mean something like Bayesian brain, and this is a little bit annoying because it doesn't help anyone, only the career of the given person. Good. Good, then let's stop here and